Greetings and welcome to Distillation. In the previous class, we discussed about recycle, bypass, and purging operations, and we discussed how and what are the scopes of material balance in these operations. All right. Now, recycle, bypass, and purging, they may be with or without chemical reactions. All right. So if they are without chemical reactions, then the process is quite easy and simple material balance would give you the answers. But if they are without, with the chemical reactions, then in that case, it would be slightly complicated and there would be one or two new terms, which I'll be introducing as we'll be going through. All right. So today we are going to discuss about certain numerical problems in recycle, bypass, and purging operations. All right. So let's go on to this example. So we have wet solid containing 70% water, which is mixed with recycled dry solid to reduce the water content to 50%. All right. Before being admitted into a granulator. All right. So let me draw a block diagram for the same. So we have a granulator. Then we have the feed. So let's call it the fresh feed over here, and over here the recycled stream is being added, and over here let's have the mixed feed. All right, and from this they are saying that the solid leaving the granulator is fed to a dryer, so it is being mixed, it is being added to a dryer over here, and from this dryer you are so dryer where it is brought in contact with dry air initially at 0.25% water by weight. Air picks up moisture and leaves with a moisture content of 5%. The solids leaving the dryer contain 20% water. So here there are solids that are leaving dryer. All right. And then they are saying that a portion of this solid is recycled. So we've taken a portion of this solid itself and we are recycling this portion of solid. Okay. We are recycling this portion of solid. Okay. And from here, we obviously have the product. All right. So this is there. So let's call this P and let's call this R. All right. That is there. Also, they have given that this is 70% moisture. This is 50% moisture. This is over here leaving, this is 20% moisture. Okay. Now, remember over here, that is this particular junction. If at this particular junction you have a separator, proper industrial separator is present here. In that case, the composition of RP and this product stream, it is going to be different, right? But if you're just taking a portion of the product stream and recycling it, so in that case, the composition is not going to be different. It's going to be the same. All right. Composition is going to be throughout the same. Okay. It's just like you have a jug full of 20% salt solution and you're pouring a glass of water out of that jug. So the composition is going to be the same. Even the water that you have poured out of the jug, it is going to have 20% of salt solution, right? So you just have to keep in mind that if you're taking a portion of this product stream, then in that case, the composition of this, and this, all the streams are going to be the same. So they have clearly mentioned for 1000 kg, they've clearly mentioned a portion of this solid is recycled. So since it is a portion of this solid, so therefore even here we'll have 20% moisture, and even here in the recycle stream we are going to have 20% moisture. All right, so that's going to be there. Okay, then let me give you information about dry air as well. So you have air, that is dry air, which contains 0.2% moisture, and you have wet air that is leaving this with 5% moisture. Okay, So yeah, this is your overall block diagram. And we are given for 1000 kg per hour of wet solid sent to the granulator. Okay, for 1000 kg per hour of a wet solid sent to the granulator, determine the following. So since 1000 kg per hour is sent to the granulator over here, so that means they have given M is equal to 1000 kg per hour. All right. They have given 1000 kg per hour of feed is sent to the granulator. So this is my M. Next. Okay. So that is your problem. And we have to determine the following things. Okay. So please hope you people are clear with your block diagram. All right. Once that is done, then we'll go on for material balance. Okay. So as I told you, we can do material balance at junction number 1. We can do material balance at junction number 2. We can do material balance for the inner unit, and we can do the overall material balance. Right. For now, let's do a material balance for junction number 1. Okay. So material balance at point 1 gives us F plus R is equal to 1000. That is the overall material balance, equation number 1. And the second equation is going to be for water balance. So that is 0.7 F plus 0.2 R is equal to 50%. So 500, right? 0.5 into 1000. So that's 500. So that is equation number 2. So when we solve equation number 1 and 2, we'll get F is equal to 600 kg per hour, and we'll get R as 400 kg per hour. All right, that is what we are going to get. F as 600 kg per hour and R as 400 kg per hour. Okay, so once we have this information, we'll move on to our further material balance. They have asked the amount of solid recycled. So we have got R as 400 kg per hour. First part has been solved. Okay. Now they have asked us to calculate the circulation rate of dry air. So we need to do our material balance about this dry air. All right. We need to do material balance about the dry air. So let's take this entire unit, granulator plus dryer, and then deal. Okay, so when we are going to take this entire unit, we'll have the green block diagram for this particular unit. I'll draw the green. This is going to be with green. Okay, so the green block diagram that you're going to have. The green block diagram that you're going to make for granulator plus dryer is going to be, the inlet is M, the outlet is, let's say P1. Let's say P1 is coming out of here. Okay, P1. And then you're going to have dry air and wet air. So dry air over here. And you have wet air going out of here. Okay. So remember, moisture lost is equal to moisture gained. Okay. Moisture lost is equal to moisture gained. So moisture gained by air is basically moisture that is present now, that is 5%, so 0.05 into W minus initially the moisture that is present, that is 0.25%. So that is 0.0025 D. Okay, this is the moisture gained by air. Okay, and moisture lost is basically 50% of M, sorry, the moisture that was present here, that is 50% of M, 500 kg per hour, minus the moisture that is present in P1, so that is 0.2 into P1. Okay, that is what we have, right? So this is for us, right? So now we have to find P1. So in order to find P1, we need P, right? In order to find P1, we need P. Okay. And again, we have S with us. So instead of just doing so much of complicated calculations, what we can do is we can make an overall material balance, right? Let me draw the entire system. So over here, yes. So let's take this entire thing. Okay. Let's take this entire thing. Okay. This entire thing. It would be easier for us to solve this problem using this. Okay. We'll just discuss how. So over here, if you see, if I'll draw this block diagram. So this is my entire system. Okay. And over here, you have feed coming in. Feed we have calculated it as 600 kg per hour. Right? We have the product leaving, which we don't know. And we have some moisture that is lost. So that moisture, instead of taking it as 0.05 W minus 0.0025 D, instead of taking this, let's take it, give a different variable E to it, right? The way we did a problem in drying, if you people would have seen that problem. So instead of taking dry air, wet air and all that, we simply took E. E is the moisture. So now this is a simple material balance problem. We have the composition here, 70% water. Over here, you have all water, and over here it is 0.2. Water is 0.2. So we are going to have the overall material balance equation. So overall material balance is going to give us 600 F is equal to E plus P, equation number 1. And the second is the solid balance equation, which is 0.7 into 600 is equal to 0.2 into P. So it is going to be so that is going to be your P. All right. So sorry. Just a minute. Solid balance, right? So this is water. See, this is the problem. This is a very common mistake. So over here, when you form the solid balance, so solid over here is 0.3 and solid over here is 0.8. So you're going to get 0.3 into 600 is equal to 0.8 into P, right? So from here, you will get 3 into 600 by 8. This is going to be P, okay? So this is going to be 225 kg per hour, okay? This is your P, okay? This is P. Then to find E, E is basically 600 minus 225, that is 375 kg per hour. Okay, so this is the water lost. Okay, then this is your water lost. Okay, so now we have moisture lost is equal to 500 minus 0.2 into P1. So from this you can get P1 as well. However, you don't need P1 really. You need the circulation rate of dry air. So now for dry air, what we are going to do, let's take this dry air again. Okay. Or let's not take this dry air. See, the water that has been added, okay, wet air that we have out, that is W, is basically dry air plus moisture added to the dry air. All right, D plus E. So that is D plus 375. That is W. All right. And then they have given us that moisture loss, moisture gain is 0.05 W minus 0.0025 D. And that is the moisture gain is 375. So we'll have 0.05 W minus 0.0025 D is also equal to 370. So from here you will get W is equal to 7875 kg per hour, and dry air we will get as 7500 kg per hour. Okay, you could have also simply solved this equation by a simple dry air balance. See, we have W equals to D plus 375, and the second equation that we have, done water balance. Instead of that, we could have done dry air balance. 0.95 W is equal to 0.9975 D. Okay, we could have done simply this balance, dry air balance. So from this over here, we would have solved these two equations and the same answer we would have. All right. So in both ways, you can solve this problem. All right. So basically, the dry air circulated is how much? 7,500. Circulation on dry basis is 7,500 kg per hour. All right. Dry. And out of that, just the dry part, just the dry air, that is air without water. If suppose you're supposed to calculate air without water, so dry air is basically 0.9975 into D, right? So that is 7481.25 kg per hour. That is your dry air without water. Okay. So if you need to calculate dry air, then in that case you get this. Okay. So they have asked you the rate of air on the dry basis. So it's not going to be 7,500. It is going to be 7481.25. Just the dry air, no wet air. All right, no water. So that is 7481.25 kg per hour. So this is how we can solve this problem. All right. So in this way, you'll get it easily. All right. We simply did material balance at 1 and calculated F and R. After that, we did an overall material balance to get P and the amount of water that is lost. Now, whatever the amount of water is lost, same is the amount of water that is gained by air. And based on that, we did material balance for air. All right. And based on that, we have got wet air out of the dryer and dry air supplied to the dryer. And then since we have to calculate dry air, amount of dry air, so there is 0.25% moisture in dry air. Therefore, it contains 99.75% dry air. All right. So 0.9975 into D gives us the dry air. The dry air without water. Okay. Without water. So that's what you have. All right. So once we're done with this, let's move on to problem number 2. So if you remember in the previous video, we discussed something about distillation, how we have a reflux that is coming in the distillation column. So we have something like that over here. So let's see this problem. We have 10,000 kg per hour, 10,000 kg of an equimolar mixture of benzene and toluene subjected to fractional distillation so as to fractionation, which is distillation, so as to produce a distillate having the composition 95% benzene and the bottom product with a composition of 96% toluene. The column is provided with a condenser in which the vapor product leaving the top is totally condensed. It was found that the vapor flow rate was 8,000 kg per hour. A part of the condensate is recycled to the column as reflux, and the other part is removed as distillate product. The vapor, reflux, and distillate have the same composition. All compositions are on a mole basis. Determine the reflux ratio on the of the column if it is defined as the ratio of quantity of condensate recycled to the quantity of withdrawn. This we'll do. So first of all, let's draw a block diagram. So this is my distillation column. This is my distillation column. In this distillation column, I'm sending 10,000 kg of feed, right? 10,000 kg of feed. Okay. And from the top, we have vapor. From the top, we have vapor that is withdrawn at 8,000 kg per hour. And this vapor, it is sent into a condenser from which you get something recycled back and something comes as distillate. The composition is same, so it contains 95% benzene. So XD is 0.95. In the bottom, you have W, which you don't know, of course, and XW is 0.04 because 96% toluene, so 4% benzene, that means 0.04. Over here, it's equimolar. It's equimolar, so XF is equal to 0.5. Everything is fine except for the fact that we have this and this, F and V in kg per hour. So we need both of them in kilomole per hour. So we know that over here, your vapor has benzene 95%, right? 95% by mole. So we are going to calculate, first of all, the first thing that we are going to do is to convert both of them, F and V, into vapor, into kilomole. All right. So we are going to calculate average molecular weight for feed. So that is going to be 0.5 into molecular weight of benzene, that is 78, plus 0.5 into molecular weight of toluene, that is 92. So this is 78 plus 92 into 0.5. Hence, the average molecular weight of this comes at 85 kg per kilomole. Okay, this is your average molecular weight for feed. Hence, feed is 10,000 kg per hour upon the average molecular weight, that is 85 kg per kilomole. Hence, we get this as 117.647 kilomole per hour. Correct. That is F. Okay. Then, similarly, we need to calculate average molecular weight for vapor. Right. So, average molecular weight for vapor is going to be 0.95 into molecular weight of benzene plus 0.05 into molecular weight of toluene, right? So that is 0.95 into 78 plus 0.05 into 92. So that is 78.7 kg per kilomole. So from this, you get vapor as 8,000 upon 78.7. That is 101.652 kilomole per hour. So we have got V, we have got F. Okay, now we can do our problem easily. Okay, so the first thing that we are going to do is we are going to form the overall material balance equation. So we are going to take this. We are going to take this entire thing in order to make our problem simple. Okay, if you don't want, you can simply form equation about the condenser, equation about the distillation column. That also works. But this is going to be easier for you to do. Okay. So when we do that, then we get two equations for the for the purple line, purple control volume. We have F, we have D, and we have W. Okay, we have XD, we have XW, we have XF, right? So we'll form the overall material balance equation. F is equal to D plus W. You have the value for F. We'll form the component balance equation. So 0.5F is equal to 0.95D plus 0.04W, right? We have again F. So when we solve these two equations, we'll get D and W. So D is going to be 59.47 kilomole per hour. And W is going to be 58.177 kilomole per hour. Okay, so that's how we've been able to calculate W and D. All right. Once we are done with this, D and W, then we can move on for our condenser balance. So now we are going to form a separate balance about the condenser. So this was my condenser. Over here, I have vapor coming in. Over here, I have liquid that is recycled. And over here, I have distillate, D. So D, we have just calculated it as 59.47. So it's 59.47 kilomole per hour. And we have V, we have calculated 101.655. So it's 101.652 kilomole per hour, right? So when we form the overall material balance equation, you will get from here V is equal to L plus D, hence L is equal to V minus D. It is 101.652 minus 59.47, right? That is 42.182 kilomole per hour. Okay, you have to calculate reflux ratio. So reflux ratio R, this is a very important term used in distillation, reflux ratio. So reflux ratio is basically whatever condensate has returned upon whatever distillate has been withdrawn. So it's basically L by D. So L is 42.182 and D is 59.47. So we get reflux ratio as 0.7. Okay, so reflux ratio is a quantity which can be greater than 1, less than 1. Okay, that's not a problem. So for now, we've got reflux ratio as 0.7. So that is our solution. Okay, so what we did in this problem was, first of all, we converted F and V from kg per hour to kilomole per hour. Once we got everything in kilomole per hour, after that, we went on to do material balance and found D and W. We made an overall control volume and we found D and W. All right. After finding D and W, we did balance about the condenser. This was the condenser balance. So once we did condenser balance, after that, we found the liquid that has been sent back. And then we found the reflux ratio. Okay. So hope this part is clear. One more equation we can form over here. See, we have not considered the column, right? So if we consider only the column, then let me draw different. So if we take the column only, then there is feed coming inside the column. There is W going out of the column. There is V that has gone from the top and there is L that has returned, right? So the equation that can be formed for the column is F plus L is equal to V plus W. Okay, and the respective component balance equations. All right, so even this equation can be formed, although very rarely we prefer forming this equation. The most preferable method is what I showed you, because obviously it's very short, right? But even this equation you can form, and then you can solve it in that manner. Okay, just the thing is, in this case you'll be having many variables. All right, so that's one of the problems. Rest, even this is manageable. All right, even this is manageable, and you can solve the problem using this particular equations as well. Okay, so once we are done with this, then let's come to recycle with chemical reactions. So if chemical reactions are involved in recycle, then, or not just recycle, let's even take bypass. So what happens? Suppose this is my unit. Okay. And from here I have my feed. Over here I have my product. Right. And this part of the stream, it is being recycled. Okay. From here it is being recycled. Okay. This is being recycled. Right. So this is F, this is M, this is R, and this is P. All right. So we have got this. So once we have got this, then there are two terms introduced for chemical reactions. Like in while we were doing chemical reactions, material balance with chemical reactions, we introduced something called conversion. Right? We introduced something called conversion. Conversion was basically A in feed minus A in product upon A in feed. Right? That is what was conversion. Right? Now over here, it's the same, but it is divided into two parts. The first type of conversion is per pass conversion. The first type of conversion is per pass conversion. Per pass conversion considers A fed to the reactor and A coming out of the reactor. Okay, A fed to the reactor minus A coming out of the reactor upon A fed. Okay, this is only for the reactor. All right. And then we have the second conversion, which is overall conversion. So overall conversion is basically, it contains this entire system. All right. So if I call this my system, then I would say that it is A fed to the system minus A leaving the system upon A fed to the system. All right. So this is for the entire system. So basically, in easiest terms, you will find that per pass conversion is basically A over here minus A over here upon A over here. All right. And overall conversion, overall fractional conversion would be A over here minus A over here whole upon A over here. All right. So that is the easiest way in which it can be explained. Okay. So that's how you have overall and per pass conversion. All right. So once we are done with this, let's move on to example number 3, which involves material balance with chemical reactions, recycle with chemical reactions, actually. Right? So it is proposed to produce acetaldehyde by oxidation of ethanol in gas phase C2H5OH plus half oxygen gives you CH3CHO plus water. The ratio of air to ethanol in fresh feed. Fresh feed is before it was mixed with the recycle stream. It is 10:1 by mole. And the conversion of ethanol on a single pass through the reactor is 25%. The unreacted ethanol is completely separated. Remember this term, completely separated. That means whatever the unreacted ethanol, it came out of the reactor, it has been completely separated and sent into the recycle stream. So overall conversion is basically 100%. All of the ethanol that has been fed, it has left the reactor. All right. It has none of that ethanol has come out. All right. So what is the ratio of the recycled stream to the fresh feed stream, and what is the composition of the outlet stream from the reactor in moles? So this is what we need to calculate. Okay. So let's draw a block diagram. So this is my reactor. This is my reactor. Then I have fresh feed over here. I have this as my mixed feed, and over here I have got recycled. Right. Then over here I'm getting whatever my product is. Let's call it P. And over here I have got P1. And all of my ethanol from unreacted ethanol has been recycled from here back. So that is there, and this is R. Okay. So that is my block diagram. Okay. So what we are going to take, we have a ratio of air to ethanol in fresh feed. Over here, it is 10:1. So we are going to take our basis. Our basis that we are going to take, it is that we have 100 kilomole of ethanol. All right. So since ethanol to air ratio is, air to ethanol ratio is 10:1. Therefore, air would be 10 times that of ethanol. So air is equal to 10 into 100, that is 1000 kilomole. All right. So that means we have 790 kilomole of nitrogen and 210 kilomole of oxygen. All right. That is what we have for air, since it contains 79% nitrogen by mole and 21% oxygen by mole. Then they have given per pass conversion is 25%. Okay. Per pass conversion is 25%. Now, all the ethanol that has been unreacted, it has been sent back. Right. All the ethanol that is unreacted, it has been sent back. Right. So therefore, we are going to get R as your ethanol. All right. R is your ethanol. So ethanol over here, ethanol in the mixed feed, is ethanol from the fresh feed, that is 100, plus ethanol that is recycled, which is R. All right. So 100 plus R, that is my ethanol in mixed feed. Okay. 100 plus R is equal to the ethanol in the mixed feed. Okay. Then it has got reacted. Fine. So my per pass conversion is 75%. That means ethanol here minus ethanol here upon ethanol here. Right. Sorry, ethanol here. So that gives you 0.25. So we can basically say 1 minus ethanol left upon ethanol fed is equal to 0.25, right? Since ethanol fed minus ethanol left upon ethanol fed is 0.25, therefore 1 minus E left by E fed. That is my per pass conversion. This is only for the reactor. This is only for the reactor. So ethanol fed to the reactor is 100 plus R. So we'll get 0.75 is equal to E left upon E fed. E fed is 100 plus R. Therefore, ethanol left is going to be 0.75 into 100 plus R. That is 75 plus 0.75 R. This is the ethanol that is over here. Okay, so since this is the ethanol that is over here, all of this ethanol is going to go into the recycle stream. All right, so basically this E left is nothing but R, since all the unreacted ethanol has come back into the recycle stream. So using this, we'll have 75 plus 0.75 R is equal to R. Hence, we'll get 0.25 R is equal to 75. Okay. So we'll get from here R as 300. Okay. R we'll get as 300. Okay. So once we have got R, then we had to calculate what is the ratio of recycle stream to the fresh feed stream. So recycle stream is R upon fresh feed stream is F. So R is 300 and F is 100 kilomole of ethanol plus 1000 kilomole air. So that is 3 by 11, which is equal to 0.273. All right, that is your A. Then in the B part, they have asked what is the composition of the outlet stream from the reactor. That means we have to find the composition of P. Okay. So since we have R, therefore we know that ethanol left is basically 75 plus 0.75 into 300. So 75 plus 0.75 into 300 is equal to 300. Right? 75 plus 0.75 into 300 is basically your 300. So that is ethanol that is left. All right. So once we have got ethanol left and ethanol that has been fed to the reactor is 100 plus R, that is 400. Okay. So ethanol fed to the reactor is 100 plus 300, that is 400 kilo. Implies ethanol reacted is ethanol left, ethanol fed minus ethanol left, that is 100 kilomole. This is the ethanol that has reacted. Now, if you see the stoichiometry, per mole of ethanol reacted, half mole of oxygen reacts. So you have oxygen reacted is equal to 50 kilomole. Therefore, oxygen left, oxygen supplied was 210 minus 50, that is 160 kilomole. Right? And all of the nitrogen that was supplied, it is left in the reactor stream, in the stream that has come out of the reactor. So basically, out of the reactor, we have number one, unreacted ethanol. Right? Number two, we have acetaldehyde. All right, acetaldehyde. So I'll call it A. Then we have water that has been produced from the reaction, right? All our gases. So we have water that has been produced from the reaction. We have oxygen left and we have nitrogen. Okay, so ethanol left is basically 300 kilomole. All right, oxygen left is 160 kilomole and nitrogen left is 790 kilomole. Now to calculate acetaldehyde and water, we are again going to go back to the stoichiometry. So per mole of ethanol reacted, 1 mole of acetaldehyde and 1 mole of water is produced. So since we have 100 kilomole of ethanol that have reacted, so we have 100 kilomole of acetaldehyde that has formed and 100 kilomole of water that has formed. Okay, so when we find the moles, when we find the total moles, this is going to be 1450 kilomoles. These many moles are coming out of the reactor stream. Okay, Then when we find the mole percent for each, so that is individual moles upon total moles into 100. So that is 300 by 1450. So 20.7%. Then for acetaldehyde, 100 by 1450, 6.9%. Even water is going to be 6.9%. Then oxygen is 160 by 1450 into 100. So that is 11%. And nitrogen is 790 by 1450. That is 54.5%. So when we add, you get 100%. All right. So this is the solution. All right. This is the solution for part B. Okay. So hope you could understand recycling using chemical reactions. All right. Make sure that you clear with material balance without chemical reactions, material balance with chemical reactions before you are doing problems on recycling, bypass, and purging. Because almost all whatever I have done in these problems is actually whatever people have already studied, right? Overall material balance, dryer, right? All these problems, means all these types of problems we've kind of done. We've just added a recycle stream here, right? Similarly over here, just added a recycle stream. Otherwise, it's simple material balance. And even over here, I give you people information about all these things. But overall, you people have majorly used your concepts that you people already brought from material balance with the chemical reactions. So if you're not clear with material balance with the chemical reactions, then it's a problem while you're studying over here. So hope you people could get what we did over here. We first of all took our bases as 100 kilomole of ethanol, and since 10:1 was air to ethanol ratio in the feed, therefore we have 1000 kilomole of air. So feed altogether is 1000 plus 100, that is 1100 kilomole. All right, that is your feed. Then we have this mixed feed. So since they have given that all the unreacted ethanol has come back, so if you have R as the recycle, so R is basically all the unreacted ethanol. So F plus R, ethanol in F plus R gives you ethanol in mixed feed. So ethanol in mixed feed would be 100, which is in F plus R. All right. After that, since the per pass conversion was given to be 25%, therefore we found out the ethanol that is left, which is 0.75 into 100 plus R. Right. So therefore, we have got ethanol left. Hence, we can get that all the unreacted ethanol, this is the ethanol left. So all the left ethanol, it is sent back into the recycle. Therefore, we have 75 plus 0.75 R is equal to R. Whatever it was left, it is sent back. So we finally got R is equal to 300. With R equals to 300, we found ethanol that is in the fresh feed, ethanol that is present in the mixed feed. All right. And we found ethanol that is left. So we have ethanol in the mixed feed is 400 and ethanol left is 300. Okay. So ethanol reacted would be 100. Right. Ethanol reacted would be 100. Then we used stoichiometry. So oxygen reacted would be 100 by 2, that is 50. Acetaldehyde produced would be 100. Water produced would be 100. Therefore, we got all whatever we had in the outlet stream from the reactor. Nitrogen would be as it is. Whatever nitrogen was fed, it would be it would come as it is. So since 1000 kilomole of air was there, so 210 kilomoles of oxygen and 790 kilomoles of nitrogen fed. So all the 790 have come in the product stream, while oxygen in 50 kilomole of oxygen was has reacted. Therefore, we have 210 minus 50 left, which is 160. So we have got whatever we have out of the reactor, and then we found the mole percent of each. All right. So hope this problem is clear to everyone. So once we are done with this, let's move on to example number 4. Now this example is about bypass. All right. So this is a problem related to bypass. So let's go through. A process stream contains 4% by weight salt and rest water. This is prepared by passing a part of pure water stream through a saturator containing the salt. And the solution leaving the saturator contains 20% salt. And this is mixed with pure water bypassed to get the process stream. So basically what we have is a particular block diagram. Let's draw a block. So we'll have this is my saturator. Then let's say I'm adding salt to it. So let's say Y amount of salt is being added. So basically the saturator contains salt, but since we need to show it properly in a block diagram, so I've just given a stream containing salt. This is pure salt. Okay, only salt. And over here you have pure water. Okay, over here you have pure water. And from this portion of pure water, it is bypassed. The remaining of the pure water, it is sent. A portion of pure water is bypassed. So as you people must be remembering from the previous video, bypass means that a small portion of it is moved such that it does not have to it does not have to pass through the unit. So it will not pass through the saturator, right? So that's there. And then we get our product over here. All right. So now the process stream, it contains 4% by weight. So here you have 4% salt. Okay. And the solution leaving the saturator, it contains 20% salt. Okay. So this contains 20% salt. Okay. So let's consider that we have X kg of pure water, and over here we have, let's P. All right, we have P kg of solution, right? So now they have asked us to calculate the fraction. So okay, let's not assume X, let's assume 100. That's our basis for calculations. So here we'll assume 100 kilomole. That's our basis. So we'll take basis that we have 100 kilomole pure water. Okay, so we have 100, not kilomole, 100 kg. Everything is by weight. So 100 kg. So we have 100 kg pure water over here. Okay, so let's assume that out of it, X goes into the saturator, and then 100 minus X, it would go from here, right? So that's what we have. So now what I'm going to do is I'm going to draw a control volume. All right, I'm going to enclose this entire thing inside a control volume. So you have to keep in mind that while we are dealing with a control volume, when we are enclosing everything in a system boundary like this, you have to make sure surrounding to system or system to surrounding transfer. If it is system to system transfer, then not allowed. So once we draw the green block diagram, it is going to have pure water over here, that is 100 kg. Then we have P coming out here and Y is fed here. Right? Y is your salt. Okay. So now when we are going to do, the first thing that we are going to do is water balance. So when we do water balance, we'll get 100 is equal to, since it is 4% salt here, therefore 96% water. So 0.96 into P. All right. So from here, you will get P as 100 upon 0.96. So that is your P would be 104.166 kg. Right, let's take it 167 kg. Okay, 104.167 kg. All right. So then once we make an overall material balance equation, so overall balance gives us 100 plus y is equal to P. P is 104.167. Therefore, y would be 4.167 kg. That is our result. Then, once we have got this y, all right, then we are going to do balance about the saturator. All right, we are going to do balance about the saturator. So I'm going to draw a block diagram for my saturator. So this is my saturator. This is my saturator. In the saturator, I'm having X kg of water coming in, pure water. Y, which is 4.167, that is coming. And then let's call it P1. So P1 is leaving with the with 20% salt. Okay. So now I'm going to do salt balance here. All right. I'm going to do salt balance. Now you people are we've almost completed material balance. So you people should be clear why we're doing salt balance. Why didn't we do salt balance here? Right. So you should be clear about these tactics for solving a material balance problem. Okay. So we have salt balance. So salt balance gives us 4.167 is equal to 0.2 into P1. So you will get 4.167 upon 0.2. That would be your P1. So P1, it comes out as 20.835 kg. Okay, so this is 20.835 kg. So now when we do overall material balance for this, we get X plus Y is equal to P1. P1 we have 20.835, and when we subtract 4.167 from it, so we get X as 16.668 kg. Okay, this is our X. Okay, this is our X. So now we basically we want to calculate the fraction of pure water available is to be bypassed through the saturator. So we have to calculate 100 minus X by 100, right? So X is 16.668. Therefore, 100 minus X is going to be 83.332 kg. Okay. Therefore, fraction of water that is available is 83.332 by 100. That is 0.8332. Therefore, approximately 83% of the water has to be bypassed. Okay, 83% of the water available has to be bypassed. All right, in order to get the required concentration. Okay, so hope you people are clear with bypass related problems. It's simple. It's quite simple. It's just a simple material balance.